To build symbolic dynamics for the horseshoe, we're going to need to do something different. We're going to need symbol sequences that reflect the invertibility of the horseshoe map. Now recall what the horseshoe map looks like, where we've got the unit square, and we squeeze it in one direction, and we stretch it in the other direction, and we bend it around. Okay, that part we know. But let's think. If we take that unit square, we look at the two horizontal strips that under the transformation stay inside, then what is happening with those two horizontal strips? And really everything in the unit square, you're getting squeezed horizontally. So if we think about what happens if you just keep squeezing, squeeze the entire square down to an interval, what do we see? Well, let's think about what happens along the vertical side of the square after we've collapsed everything out horizontally. We have those two horizontal strips, the lower one and the upper one, that under the action of the horseshoe map get stretched out to be vertical strips. But collapsing everything over to a vertical interval, what we find is that these two subintervals get stretched out over the entire interval. And if we were to map out what was happening, just like it was a one-dimensional map of the interval, then what we would find is something that is very similar to a tent map. And recalling the way that we set up symbolic dynamics for the tent map, where we have the first interval being labeled 0 and the second interval being labeled 1, well, we could pull that back to the entire square for the horseshoe map. And those little subintervals, 0 and 1, become these horizontal strips. Let's label these strips 0, 1, or better yet, let's label them H0 and H1 for the horizontal strips, since we've got a lot of different strips going on in the horseshoe. Now, this is all very good, but we need to consider the inverse of the map as well. Now, what happens in that case? In that case, if we take that unit square, we can think about the pair of vertical strips that arise in the image of the horseshoe. And if we apply the inverse, it undoes what the horseshoe does. It takes those two vertical strips back to the original horizontal strips H0 and H1. Now this inverse stretches in the horizontal direction and squeezes in the vertical direction. So if we think about taking that squeezing action and just collapsing the entire square down to a horizontal interval, then again what we see is something just like the tent map, where we have these two sub-intervals that get stretched out over the entire horizontal interval. So it's as if we've got a pair of tent maps acting here, one horizontal and one vertical, if you will, corresponding to the inverse of the map and the map itself. Now, why are we doing this? Oh, all of this serves to motivate the symbolic dynamics, or the itineraries, for points in the horseshoe invariant set that we can now fully describe. Here's the setup. Given a point x in the invariant set lambda for the horseshoe map, we're going to define I of x to be the itinerary, the symbol sequence of x. This is going to be a symbol sequence whose digits are in the set 0, 1. But instead of raising that set to the power of the naturals, we're going to raise it to the power of the integers. What do I mean by that? This itinerary is going to have a decimal point, and then its digits, A0, A1, A2, A3, A4, A5, keep going. All of those digits being zeros and ones. That's fine. That's what we did for the non-invertible tent map, or doubling map. But now, we're also going to have digits going the other way. We're going to have a -1, a -2, a -3, a -4, keep going. All of these together form a bi-infinite sequence of zeros and ones. Now, the way that this is going to work is this is going to tell you, again, with all the symbolics we've ever done, roughly where you're at in the 0 zone or the 1 zone. And that first digit after the decimal point, A0, that's going to tell you where you are now. A1 is going to tell you where you're going to be tomorrow after one application of the horseshoe map. Keep going, keep going. The future is encoded off to the right. But to the left, the digit A-1, that tells you where you were yesterday. Or, if you like, what happens when you apply the inverse of the map. Keep going further and further into the past. That's how we're going to use symbol sequences to encode the dynamics of a point in the invariant set. Now we're almost done. All we have to do is say exactly how we're programming these sequences. We're going to operate via the following rule. Everything is going to be based on these two horizontal strips in the original unit square. Recall we labeled them H0 and H1. Here's how we program the digits. The nth digit, A sub n, in the itinerary is either a 0 or a 1. It's a 0 if the nth iterate of the horseshoe map applied to this point x lies in the horizontal strip H0. The digit is equal to 1 if the nth iterate of this point x under the horseshoe map lies in the strip H1. Now this works for any value of n. If n is 0, that means you do nothing. It's just where x is. If n is positive, you're applying the horseshoe map that many times. If n is negative, you're applying the inverse horseshoe map that many times. Now, this might look a little complicated. It's really rather simple. You could compress all this out to rephrase it as saying the nth iterate of x under the map F lies in the strip H, whose subscript is the nth digit. So it's H sub A sub n. Now, that's a little complicated to say, but to write it out, it's really compact. Now, whichever way you prefer to remember it, doesn't matter. It's all good. The important thing is we now have itineraries for points in the invariant set, and we claim that this is the key to understanding the dynamics of the horseshoe map. It's going to take a little bit of time for us to work out the proof of that. But for now, focus on how you define those itineraries or symbol sequences.